So having discussed about the link between the thermodynamics and statistical physics through Boltzmann idea, where he considered equilibrium is that state. So he thought about that equilibrium is that state from the statistical point of view. It has got the most probable state, or the or the state which has got maximum probability, whereas from the thermodynamics point of view, it has the state which has got maximum entropy. So let us just now establish this idea mathematically. Okay, so according to thermodynamics, the entropy and temperature are related through this relation. So we all know about, we must have seen in earlier thermodynamic classes as well. So basically, if I have to write it, you may be familiar with the del E equal to del T del S. So you may be familiar with this. So just rearrange the terms and is written like this. Okay, so now from the discussion that we had, the 1 by T is equal to K beta. Okay, so we can and from the statistical, so we have seen just a few minutes back that beta is that parameter which remains constant in thermodynamic equilibrium, and is given by this particular. So beta is equal to that parameter, which is given, beta is equal to del ln W by del E, where this W is thermodynamic probability, or the number of microstates. So I have just substituted beta for this, so you get particularly this expression. So you know that the left hand side 1 by T, both of these are equal, so I can equate this both this expression, and which will end up giving me this particular expression. Okay, so I will end up getting this particular expression. Nothing I have done, I have just equate this from the above. Let's say this is equation maybe say 1 and this is 2. Using this 1 and 2, we have got this expression. So now if I integrate both sides, okay, so then I will end up getting this particular expression. Okay, so let me just highlight this part. S equal to, okay, so S, which is entropy, and K is some constant. I don't know what this constant, but this is K is some constant, then ln W. Okay, so this is Boltzmann entropy relationship. Okay, so basically, see, the entropy is from the thermodynamics side. Okay, so this is the parameter or the thermodynamic variable of a system from the thermodynamics, and the W is completely from the statistical mechanics, which represents the thermodynamic probability. So this shows that entropy is directly proportional to the ln, or the logarithmic or the log of the W, which is thermodynamic probability. Okay, now the same idea can be extended from another point of view. The Boltzmann had this idea where, again, this will establish this expression, okay, using, let's say there are so the Boltzmann assumed that, you know, the entropy of a physical system in a definite state of a function is a function of the maximum probability. Yes, of course, we have just seen that there has to be some kind of relationship between the entropy and the maximum probability, because that's what the idea which was linking between these two, thermodynamics and statistical physics. So we can say that entropy of a system is related, or is a function of maximum probability, or it is related to the thermodynamic probability. Okay, so I can write entropy S is equal to some function of, let's say, W is here, this is thermodynamic probability. Okay, so thermodynamic probability. Okay, so now let's consider two independent system, completely independent system. Let's say this is my one system, okay, and this is another system, okay, completely two independent system. This is, let's say, system A, which I call it, and this is, let's say, system B. Okay, and this has got entropy S1, and this has got system the entropy S2. So then both of them are completely independent, and we know that entropy is extensive quantity. So if I consider this system together as a whole, okay, so this is now my new system. You get the combination of two systems. So the total entropy of the system will be the sum of the individual entropy, and so that's why S is equal to S1 plus S2. This is from the basic thermodynamics that we have studied in earlier classes as well. So now, so I can write the, so let's say again this, so basically here I can write that this is function of f of w, okay, and let's say w1 be the thermodynamic probability of the system A, okay. Similarly, we can have w2 be the thermodynamic probability of system B, okay. So then, since now these systems, two AB systems, are completely independent of each other, so the total thermodynamic probability will be given through this. So these are like joint probability. So I can get that the W is the thermodynamic probability of the entire system. That means that considering both the system together, which will give me the product of the individual thermodynamic probability. Okay, so that's how it is given here. W is equal to W1 cross the multiplied by W2. Okay, so then we can write this S is, as I have written in the previous slide, S is equal to F of W, and this W as given by from this earlier expression, which is this. So finally this is related to F is a function of W1 cross W2, and individually S1 is, you can write the function of W1, S2 is function of W2. Okay, now just substitute all this expression that we have got in terms of the function W1 and W2 in this particular expression. Okay, so take this, all these things, all this individual stuff, and put it here. Okay, so what I will get here, so this is so this was S, if I have to repeat here what has been written in the previous slide, and this is S1 plus S2. Okay, so I have just substituted for S1 and S2, and I have represented here. So in this expression, what do we do in this expression? Okay, so in the left hand side, the function is, so the function f is a function of W1 and W2, and the right hand side, the first term is function of only W1, okay, second term is function of only W2. So I differentiate partially with respect to W1, entire, both sides, left side and right side. So since this function is a function of both W1 and W2, so since I am partially differentiating with respect to W1, so then the W2 is a simple differentiation, so W2 will come out, so that will be constant now. And in the right hand side, the second term will give you 0, right? So second term will be 0 because that is independent of W1, and this f dash of W1 is a differentiation of W1. Okay, similarly differentiating this expression again is, okay, so this expression with respect to, let's say now W2, okay, so what we will again get, that W1 multiplied by f dash of this W1 cross W2, then equal to f dash of W2. So this is simple stuff, right? So first thing we have differentiated with respect to W1, second thing we have differentiated, so second time we have differentiated with respect to W2. So let's say again this is my equation, maybe I don't know what name to give, but this is 1, let's say this is 2, and now divide, let's say 1 by 2. Okay, so if I divide 1 by 2, so I will end up getting, let's say, so I will have here, let's say 1 on top, so W2 f dash W1 cross W2 divided by, I will get W1 f dash W1 cross 2 equal to f dash W1 W2. Okay, so you must, so now you can see that this particular expression here, this is there in the denominator as well, so that will cancel out. Okay, so we will remain with this particular expression. Okay, right? Okay. So from here I can do one thing. I can rearrange the term and write. Okay, so I can rearrange the term such that W1, so I have taken W1 to the left hand side, so it will be F dash of W1, then right hand side you will get W2 multiplied by F dash of W2. See, from this expression, so even if I had, so I can extend this idea. Okay, so even if I have, let's say, third system, which I like, you know, in the first thing when I consider two independent systems, even if I have third system, if I carry out this exercise that whatever we have done, then probably we will get there will be one more term which will give me, let's say, W3 F dash of 3, right? Yes, we may get that. Okay, so we can write essentially it's the thermodynamic probability of that function, okay, sorry, that system multiplied by the derivative of the entropy function that was, which was function of the thermodynamic probability, right? So, and this expression for each of the individual system will be, let's say, equal. Meaning what I'm trying to say, even if we have, let's say, n systems, so I can write that Wn, the F dash of Wn would be equal to each one of the system. So I can write this as some constant, isn't it? So let's say some constant k. So each one of them I will write some constant k. So yeah, so exactly this I have written here. Okay, so this is, let's say, some constant k. So again I can rearrange this term. So if you take the first term, let's say first term which is equal to k, then I can rearrange, right? F dash of W1 is equal to, so k by W1. Similarly, F dash of W2 equal to, so I can, if I had, let's say, third system, I could have written like, you know, F dash of W3 would be equal to k by T. Okay, so since there is a derivative in the left side, I can integrate with respect to, you know, W1 as my independent variable. Okay, so if I integrate, so then I will end up getting, so let me just write this. So I had F dash of W1 equal to k by W1. So if I integrate this, so I will end up getting what? This particular term, right? So if I, after integration, we will get this, where the C1 is the integration constant. Similarly, for the other expression which I had, F dash of W2 k divided by W2, I will end up getting this second expression. Okay, so if I had another system, so it will be F3, so F of W3 and same k ln W3, and it will so on and so forth. Okay, so in general I can write this particular expression. Okay, so in general Fw is equal to k ln W plus C. Now try to, so now we shall try to calculate this integration constant C. Okay, so what you do here is that at temperature absolute 0, okay, let me use red color here, let's say at temperature absolute 0 Kelvin. So in that sense I have, so all particles or molecules are in a ground state, so I have only one state in that. Okay, so thermodynamic probability for that case will be 1. Okay, and of course the entropy will be 0 in that case, so S will be 0. Okay, for this region, so I can now, using all these things, I can find out the C if I substitute back all these things in my expression here. So this Fw is what? This is S, right? So S is, so 0 equal to, so k ln 1, which will be again 0, and C, so it will end up getting C equal to 0, the integration constant which is equal to now 0. So I will end up getting, so the same thing is written, so the constant C can be evaluated. Okay, therefore so I end up getting this particular expression, and this is Boltzmann entropy relation. Okay, which again, just to repeat, says that entropy is directly proportional to the logarithmic of the thermodynamic probability. Okay, so and this is the expression which actually bridges the thermodynamics and statistical mechanics. Okay, because W, which comes from the, you know, thermodynamic probability, it's the number of microstates for a given macrostates, right? Whereas in the other side you have entropy, which is a thermodynamic quantity. All right, so let's continue our discussion. Okay, now we'll start studying this Boltzmann canonical distribution law. Okay, so what happens in equilibrium, let's say. Okay, so let's consider a system in equilibrium having this so now we have to understand that, see, we have this phase space of a system which we have studied in earlier slides, right? So let me just get back to, this is my, let's say, phase space, just to represent. So phase space is, in this case, it is 6-dimensional, right? We all know. So this is, let's say, x, this is, let's say, px, which you have learned. And now we have divided this phase space into various smaller compartments, right? Smaller boxes which I see, which are of equal size, and we call them in earlier videos as cell. Okay, so these are like just a representative. Okay, so each one of these cells are of equal size. Okay, so let me just put one cell, let's say. Okay, so this is, let's say, so this I call it cell. Okay, which we have discussed in earlier videos. Okay, so this is my cell. Okay, so now what do we do? Let's say that we consider a system in equilibrium and having this n1 particle in, let's say, cell number 1. Okay, and there's a n2 particles in cell number 2. So cell 2, now cell 1, and this, just imagine this cell 1 has got energy E1. Okay, so if I have to just summarize here, or just to write cell 1, let's say cell 2, I'll write just 2 representative cell. Okay, let me write cell I. So I'm just numbering these cells. Okay, so in cell 1 I have n1 particles, and each of them, so the energy is E1. Okay, similarly I have cell 2, which is number of molecules or particles there is n2, and then energy is E2. Similarly we have the ni number of particles or molecules here, and Ei is the energy corresponding to that cell. Okay, so now in equilibrium we know that it is most probable state. So what we will do, there will be a system is trying to be in that equilibrium state. So here one thing is here, the total number of particles for the entire system is constant. However, what will happen, these ni's will try to, because it's a gas molecule, they are continuously moving, this is a dynamic system, so there will be change in the number of particles for a cell. If you consider a particular cell, there could be like change of number of particles. However, the changes will occur within this cell such a way that this entire state of the system does not move away from the equilibrium state. Okay, so it will be very close to equilibrium state. Maybe from some particles from the cell number 2 is going to, let's say, cell number 100. Okay, so from 99 some will move, but that movement or the change in the number of particles in the cell will be such a way that the system overall it remains in the equilibrium state. Okay, so right, so getting this idea taking forward. Okay, so at any instant, as I have said, the gas molecules obey the following fundamental postulates. Okay, so let's try to get one by one. So one thing is that, as I said, total number of particles is constant, whereas, so I just sum all the so the number of particles in each of the cells, which let's say add up to n. Okay, this is constant. Okay, and since it is constant, so if there will be no change in the total number of particles, so I will end up getting this del n, which is number of change in the total number of particles, which is 0. However, there could be some change in delta n1 or delta n2, delta ni. There could be, and as many numbers as you are considering for your study these cells. So del n, the capital N, the total number of particles which is referring here is constant, meaning yes, so that's why del n is equal to 0. However, this individually del n1, n2 not necessarily be 0, but the changes will be, so the gain in someone will be loss in somewhere. Okay, So the loss in somewhere will be gain in somewhere, but all of them, if I add it up, will be equal to 0. Okay, so there will be some exchange of particles among the cells. Okay, however, the total number of particles, so the total changes that if we add it up, it will be equal to 0. Similarly, the total energy of the system is constant. Okay, so as I said, total energy of the system, how will I get? E1, so number of particles in cell number 1 is N1, so multiplied by E1, which is the energy corresponding to cell 1. So similar, so we'll get the total energy corresponding to cell 1, then the cell 2, cell I, and similarly all of them I add up, I'll get total energy. Okay, so that will be again constant. Okay, so these are the two fundamental postulates which we have studied under the fundamental postulates of statistical mechanics when we apply for gas system. Okay, so similarly, since this del E will be 0 as this E is constant, however, there could be some changes as I said in the just few minutes back. Okay, del N1, N2, Ni, all there could be changes, but overall changes in the energy will be 0. Okay, so this E1 is constant, E2 is constant, so this E1, E2 represents energy of that particular cell. Okay, so that will be constant, however, there could be exchange of particles among the cells which we have. Okay, now since we are in equilibrium state, so we are considering here now system is in equilibrium state, so the thermodynamic probability will be maximum, as you will know. And when we have this, first derivative or the total differentiation corresponding to the W will be 0, right? So then we can carry out the maths related to that. However, here see, we all know that this W expression, the thermodynamic probability, is extremely huge number, right? It's because, and it of course depends on number of particles in the system. And we all know, whenever we're considering the gas, we know that 1 mole of gas itself is, has got number of particles in order of 10 to the power 23. So imagine how many, and then taking factorial of that, it will be huge number. So what we will do, instead of considering W as it is in its magnitude, we will take logarithmic value of W, okay, which will reduce our, or like, mathematically it's easier to deal with. Okay, so when I say W is maximum, so the ln W will be also maximum, right? When I say is maximum, and we can have the same case that if it is maximum, then I can say that del ln W is also equal to 0, is one and the same thing, right? Okay, so that's what we will do. Okay, so now see, the thermodynamic probability expression we have, in one of those videos we have calculated for when we considered, try to calculate number of microstate for a macro state, okay, of unequal compartments, where we considered again each one of the compartments we have made some cells. Okay, so now in that case, now here see, in the phase space all cells are equal size, so the expression for thermodynamic probability for the total number of particle n is given by this particular formula. Okay, so this is for equal size compartments, right, or the equal, so all here cells are like now compartments which are equal size. Okay, now so we'll take, as I said, W is a really huge number, so we'll start using we'll take a logarithmic of both sides. So it will, by taking natural log on both sides of this expression, so we get ln W. Okay, and then on top we have, so here we have applied, like, ln, all of you must be knowing this, ln A by B, it is formula is given ln A minus ln B. Yes, so this particular formula we have applied here. So your ln factorial, and so ln n factorial, and then remaining whatever is there in the denominator, all will be subtracted from the previous one. Okay, so like this. Now again, this n, as you all know, that this is pretty large number, so we'll make some approximation using what is known as Stirling theorem or Stirling formula. So whenever this number is this x, here you can see when it's pretty large number, okay, and you have to take factorial of that, so ln factorial is so ln x factorial is given by, so you can approximate the value of this number is equal to x ln x minus x. Okay, so let's apply this particular formula in each one of these cases. So ln n factorial will become, so this term will become, okay, so this will become n ln n and then minus n. Similarly, let's say for this it will become n2 ln n2 minus n2. This will become like this. Similarly, you can write for all of them. Okay, so I have written it here. So if I just expand all these things, so these terms come from ln n factorial, this term comes from ln n1 factorial, right? So ln n1 factorial here. So similarly from the ln n2 and then ln ni factorial. So as you can see, so the second term onwards I can write in a very short form like this. So I can use summation for all the terms. Okay, so I going from, let's say, 1 to up to whatever number of cells we consider. All right, so now what is the idea? So we are in equilibrium, so the del ln w has to be equal to 0. So so let's try to find out this ln del ln w. Okay, so you see, so I have to take derivative of this and derivative of this term. Now since the n is constant, this capital N is a constant number, so if you take derivative, it will be just end up giving you 0. So this particular thing, there is, it will end up giving you 0. So we can ignore that particular thing, particular expression. And then now we know that del ni individually is not 0. Okay, this is individually if we consider not equal to 0. However, if I take sum of all these things, then it will become 0. However, individually not 0, but if I take sum over all of them, then it will end up, because sum of this del ni will give you this change in total number, which is not so change in total number is not so there is 0. Okay, so because the total number is constant, total number of particles in the system is constant. Okay, so here again you can apply a chain rule, right? Del, so there are two terms. So ni is multiplied with ln ni, so you take ni to be constant first and then take del ln ni. Similarly, so this is the first one, so you are applying chain rule, so keep this ln ni constant and then del ni. So and then the last term you have del ni. Okay, so now if you take derivative of del ln ni, you will just giving 1 by ni. Okay, and so this ni comes here, this comes here, then del ni will be there from, right? So the 1 by ni, then del ni from this derivative of this particular term, and as you will just you substitute back. Okay, so now this ni, so let me just clear up a little bit. Okay, so yes, so now this ni and ni will get cancelled out, and then now see you left out with del ni, and this is negative del ni, so both of them will now again cancel out. I will end up having only this particular term with the summation. Okay, so we ended up having only this particular term, and which means that if I expand this particular term, we will end up getting this. Okay, so del ln w ended up giving me, right? So del, so I need to write it here, the del ln w ended up giving me okay, which is equal to 0. As after putting this equal to 0, I got that sum of I ln ni del ni equal to 0. Or if I expand this, okay, I get this particular expression. Just let me put in some different color, because I will be using this particular expression in near future. Okay, okay, so I end up getting this particular expression. Now I need to put a little bit a mark on this. Let's say this expression is for me okay, let me put just some a. Okay, let's say this expression is a, and let us remind ourselves we had also this expression. So this is expression a. Okay, let us remind ourselves the expression, this let me use same color. Okay, so this is another expression which is equal to 0. Let's say this is my b expression. Okay, I'm naming it because I'll be using it. Okay, so now Let's because I will need this as well, so let me clean up, and then ended up doing this. I'll be using this particular, let's say this is okay, so this is my, let's say, expression C. Okay, so see, in A, B, C, all three expression are in the right hand side, it is equal to 0. So these three equations, so I can use, okay, Lagrange method of unknown multipliers and get out some information regarding that. Let's try to do that. What, okay, well, I'm trying to say, okay, so you take, so this is your expression, what I have considered is A, right, isn't it? So this is your expression A. So I multiply the expression A with, let's say, one constant, which is lambda 1, okay, and the lambda 1 is not equal to 0, okay. So and then we have taken this expression B here, right? So I have multiplied this with the expression B with lambda 2. Okay. Similarly, the expression C I have multiplied with this lambda 3. Then lambda 1, lambda 3, all these are some constants. Okay, some unknown constants. Okay, and since each of this A, B, C expression, all of these are anyway it's 0. So multiplied by any constant will end up 0. You add them, all of them, it will still be 0. So it will just end up giving you 0. Okay. Now, you know, this is the way how to progress with this Lagrange method of unknown multipliers. Okay. So now, what do we do? Let's divide this. So this is, see, this is continuation of this. Okay. So I am adding all the three expressions. So this is being added here. Or this is like one same expression. Okay. So each one of this, what I do, I just divide the expression A, B, C. So all them are in single line. So entire, let me just clean up to right here. Okay. So entire expression, what I do here, I divide by, let's say, okay, I divide by entire expression to lambda 1. Okay. So if I do that, I ended up getting the lambda 1, you know, the lambda 1 here after division by this lambda 1 will just ended up getting 1. Okay, and then we have, so the second expression will be divided by lambda 1. Similarly, we have this particular expression, and then this is lambda 1 dividing this lambda 3. Okay, now again substitute for this lambda 2 by lambda 1 equal to lambda, and a lambda 3 by lambda 1 equal to beta. Okay, these are again some new constants. Okay, so after substitution we will get, so there is 1 here, right, and then lambda and then beta. Okay, still right hand side is equal to 0. So now what we can see here, so there is also delta 1, delta n1, here is also delta n1. In the third expression also we have delta n. Similarly, delta n2, then delta n2. Okay, so I can find same number of expression in each of these meaning terms that I have written, A, B, C that I have written. Okay, so I can rearrange this thing, meaning what I can write, I can take common, let's say I take common, meaning the ln n1 I can write plus lambda plus beta e. Okay, then I can take common this delta n1 common. Similarly, I can write the second expression to be ln n2 plus lambda, then I have beta e2, and then take delta n2 common. Similarly, I can carry out all the way. Okay, I can have ln ni plus lambda plus beta ei. Okay, this lambda and beta, these are unknown constant. We will do exercise to find out what is values of this constant after getting this Boltzmann canonical distribution law. Okay, so I can keep getting, so this is like common I will take is ni, and this I'll keep taking, and then equal to 0. Now here see, as I said, this delta ni is the delta ni. So if you take delta n1, delta n2, n3, n4, all these things, these are independent of each other. Okay, so this expression actually you can think about a linearly independent expression. Okay, So whenever we have a linearly independent expression, so what happens in that case, coefficients itself has to be equal to 0. Otherwise there is no option. Okay, if the expression is linearly independent, each of this term, okay, because this ni, n2, so because the change in n1 is independent of any of the change in any of the change in number in any of the cells, because this is a random process, right? Okay, and so this coefficient, each of this coefficient will be equal to 0. Okay, so I can write in general, let me just write it in general. So in general I will end up getting, and so in general I will have this ln ni plus lambda equal to 0. Okay, so because this n del ni is independent of each other, meaning the linearly independent expression, so their coefficient has to be equal to 0. Okay, now if I rearrange these terms, okay, so ln ni equal to minus, so if I take these terms in the other side, so beta ei, okay, so then I can write ni, so if I take antilog both the side, it will be e to the power lambda minus lambda beta ei, okay, and then I can write e to the power lambda minus lambda, then e to the power minus beta e. Okay, so let me just get this side so that I can write some more stuff. Okay, okay, and this I can write, let's say this particular thing, this expression I call it, let's say a. Okay, so I can write this is a e to the power beta ei. So basically I end up getting this ni equal to, okay, a, which is a constant again, and e to the power minus beta ei. Beta is also constant, a is also new constant now. Okay, which I will, so I'll end up getting this particular expression, and this is known as, you know, this Boltzmann, this is, so let me just, e is missing here. Okay, so this is Boltzmann canonical distribution law. Okay, now let's try to understand what does this. So ni represents what? Number of particles in the cell number I. Okay, a is constant, beta is also constant, we don't know what these are. Okay, and then ei is the energy corresponding to that particular cell, and this is a exponentially decaying function. Okay, so if I have to plot this particular function, let's try to get it here. Okay, so let me just try to plot this expression. If I start plotting this expression, so it will be like an exponentially decaying function. Okay, okay, so where, you know, you have expression, so this is will be your ni and this is your s-axis is your ei. So this tells you that there are more number of particles for the zero energy state. So as the energy is increasing, so number of particles in the high energy state is decreasing. That's what it indicates from this plot as well. But you know, this doesn't mean that your number of particles are less in so the particles having high energy will be less. Okay, it's just that fact that, you know, so number of cells for the high energy is also much higher. Okay, so it's some kind of, it's representing a number density. Okay, so which is, you know, because in the ground state or towards the low energy state you have more number of the less number of cells, so that the occupancy of these cells is more compared to the high energy energy state. So that's why this plot looks like this. Okay, okay, just to repeat, so it may look like, you know, that, you know, the number of molecules having zero energy is more than any other energy, but it is only the fact that there are more number of cells at the higher energy. Okay, so that's why it is like that. So this plot shows this. Okay, and this ni gives you the distribution or the number of particles that will occupy at different energy states. Okay, so this is what you obtain is your Boltzmann canonical distribution law. Okay, now it may happen that the various cells that exist, the adjacent cell in a phase space may be of nearly same energy. Okay, so those number of cells which, so we call it, so this let's say there are GI number of cells within a particular cell which are having nearly same energy. Okay, so this we call it zone of cells. Okay, a group of adjacent cells in a phase space with nearly same energy. Okay, if GI is the number of cells in a zone, okay, so then the probability of finding the molecule in that zone will be proportional to GI. Of course it will be, because more number of zones, so the cell in the zone, then the higher probability of trying to find the particle, and this GI is called as prior probability. Okay, so then the number of particles or the molecules in the zone will be given by this A. See, there is this factor GI has come into the play now. Okay, so earlier we had only Ni equal to A. So for a particular cell we had A and then e to the power minus beta E. But however, whenever we have for the zone, because the zone consists of again a GI number of cells again, so then the GI will come into play. Okay, so next let's try to talk about how to find out this value of the constant A. Okay, now we know that Ni represents what? This number of particles in each cell. So the sum of all Ni's must give you the total number of molecules, the capital N that we have talked about. Okay, we have started with. So sum of Ni will be giving you N. Okay, and this is a simple expression. Okay, so now which is A, and then because this is sum of I involved, so this particular expression is known as partition function. This is very important. Okay, this is known as partition function. It is also known as sum of states. Sum of states. Basically, it's summing up how the energy is being partitioned in different cells. Okay, with some factor e to the power minus beta E. Okay, so it's called a partition function. Somehow it's related to how energy is being partitioned or divided in various cells and things like that, how that it is distributed. Okay, so this partition function will play a very important role in a lot of the observables or the meaning the thermodynamic variables we will try to calculate in the system. Okay, so now here we are trying to find out the value of or the expression for this constant A. Okay, so then what do you do here? So this put back so here, yes, the partition function, this particular expression, you can write I or you may not write. So this is typically represented as Z. Okay, maybe some other people will use some other expression, but it's up to you. So whichever you like you can use. So this is Z. So then I can write N is equal to, so N A, so then Z. Okay, so N is total number of particles, A is your constant which we are behind, and then Z is your partition function. So as simple as, so A is given by N by Z, and if I expand this expression, so it will be given like this: Ni equal to N by Z, which is A, and expression given like this. Okay, now we have got the values or the what the expression for this constant A. Now let's try to find out for the beta. Okay, so now let del Q amount of heat is being supplied to a gas at constant volume. Okay, so that what happens, some molecules from the lower energy can move to the higher energy state. Of course, if you supply some energy, some molecules from the lower energy cells will move towards the higher energy cells, of course. And means what? So there will be change in this number of particles within the change, so within the cells. So let's say Dn1, Dn etc. So these are the change in the number of molecules in cell 1, cell 2, cell 3, and so on and so forth. Okay. So to find out this constant beta, so what we have done, we have supplied some, let's say del Q amount of heat. Okay. And so there will be some exchange of, so the molecules from the low energy state will go to high energy state. So there will be change of this number of particles in this. Okay, still the total number of particles will be the same. Okay, meaning it will be constant for that system. Okay, so so then what you will get, so dE, the energy of the system, which is equal to the there's a change in the energy of the system which is equal to the del Q which is the amount of heat supplied from the outside, and we know from thermodynamics that this is equal. I mean this expression is equal. Okay. So equal. So from here I can also get an expression. Let me just see that what I can write. 1 by T will be equal to ds by d. Okay, I'm just writing this because this may be useful in the later slides. Okay, so so now the change of this energy will be reflected. How there will be this dE, we all know that this E1 D1 from the second postulates or second fundamental postulate of statistical mechanics. We know that there is dN, dN1, dN2, di. There could be some changes, but which will end up getting the change in total energy. Okay, and which I can write as a sum of EI dNi. Okay, so let's now now also from the Boltzmann entropy relation, we know that the entropy is related to the thermodynamic probability, which is S equal to K ln W, and if I take derivative of that, then K d ln W. Now this W, again we know from our earlier expression, W was equal to n factorial, n1 factorial, n2 factorial, all the way ni factorial. And from there, when I take this ln, and after taking ln, you take del ln, and we ended up getting this particular expression. Okay, and also we have taken that if you take derivative of what a total differential of this system, so this part is constant, which end up getting 0, and then we ended up getting this particular expression. Okay, so if you can go forward and you can go back to the time point where I have discussed about this, and you can verify this expression. Okay, so you can check back your expression. Okay, so then ds that we are trying to calculate here mathematically will end up getting, so I substitute for this ni here. Okay, so ni, you will know that just now from the Boltzmann canonical distribution law, ni is equal to a e to the power beta ei. So let's substitute back here. Okay, so I have substituted for the ni. Since there is a ln here, so ln a and then minus beta e. So ln and e is there, so that will end up giving me, it's simply beta e multiplied by dni. So see, this is simple maths, so this will end up getting this, then from this particular expression we will end up getting this. Now we have seen this particular expression. Okay, so dni may not be equal to 0 because there could be some change over, but over, if I sum them up, it will be equal to 0. So this particular expression is equal to 0. So this is giving you 0, and this just now we have seen that this is equal to d. Okay, so this side it is ds. So ds will end up getting what? ds will be k beta de. Okay, so now ds by, I have written just a few minutes back, which I thought it will be useful. It will be, is from according to this expression is k beta, and this is equal to 1 by t. Okay, so that means what? So that's what, this k beta is equal to 1 by t, or beta equal to 1 by k by t. So this is the expression what we had earlier as well, right? While trying to relate this statistical mechanics and thermodynamics. So we get the same expression back now. So beta is equal to 1 by kt. Okay, so k is constant here, and then t is your temperature. So we have obtained the expression for A as well as for the beta. Okay, so now then we can write our the number of molecules in a cell. So expression for Ni we can write completely now. Okay, so the beta, I just substitute for beta. Beta is 1 by, so beta is 1 by kt. Okay, so I just substitute for the beta, then I ended up getting this particular expression. Okay, so the number of molecules in a cell having energy Ei will be given by this particular expression, Ni equal to A e to the power minus beta E and then beta is 1 by kt. Okay, now the probability that a molecule will possess energy EI will be, now see, I know Ni number of particles are present in EI, meaning the ith cell which is having energy EI. So the probability that a molecule will possess energy EI, so it will be given by what? So there are total number of particles, capital N. So out of the Ni, there is a small Ni, particles are having energy EI. So the probability will be given by, pretty simple, right? Ni by Ni, small Ni by capital Ni. And so the Ni expression you all know, just substitute. So then we will end up getting, let's say, some, this A by N is some constant which is, I call it C. Now let's try to find out this, what does C is. Okay, we all know that the probability, the sum of probability of having energy EI, if I sum up all the probabilities, should be equal to U1. There is basic statistical, statistics theory, you all know that. So take sum over, so a substitute for pi from here, from this particular expression. So right hand side will end up getting this, left hand side, the sum of this probability will give you 1, and then we have other side, we have this. So from this particular expression we get C equal to 1 by, so e to the power EI kt. So what is this actually? This is your partition function, right? That's what we have got, a sum of EI beta, in that case we have written. Okay, so this is your Z. Okay, so if I substitute back for what C we have got here, okay, so the value of C that we have got here, substitute back in this particular expression, then we end up getting this particular expression. Okay, so what we must remember now, this probability of a molecule possessing energy EI is given by this particular expression. Okay, and the denominator that we see here, that is a partition function. All right, so let's stop here.